Welcome to A-level physics looking at wave-particle duality and electron energy levels. So light, which you thought was a wave, has got the properties of particles in certain situations. The answer is it is both. You have to treat it like a wave to explain what happens to it as it travels or propagates, and you have to treat it like a particle to explain what happens when it arrives at the surface. If waves sometimes behave like particles, couldn't the reverse be true? Well, a man called Count Lewis de Broglie thought so. He did the experiments that showed that you could make particles like electrons diffract. Since then, other particles like protons, neutrons and alpha particles have been shown to have wave properties too. To explain the wave behaviour of particles, de Broglie developed an equation that answers the question, if electrons are behaving like waves, what's their wavelength? It is lambda equals Planck's constant divided by the momentum of the particle. Lambda equals h over p. So now we're going to look at electron energy levels. The sun should produce pure white light, i.e. light from every frequency should be present. But study the spectrum produced by the sun and you get gaps on it where light of particular frequencies are missing. Why? Well, the light leaving the sun has to pass through gas clouds at the surface of the sun. All the photons of a particular frequency and therefore a particular energy are absorbed by the gas. In fact, they are absorbed by the electrons in the gas atoms. The reason for this is that electrons can only exist in atoms in certain energy states or levels. Like books on a bookshelf, you can't have electrons halfway between one level and the next. To move from one level to the next requires set amounts of energy. Photons with these amounts of energy are the ones absorbed by the gas. Other photons with more or less energy than these values are left untouched. Hence you get lines which are gaps on the spectrum where photons are missing. We draw energy level diagrams like this. N equals 0 is ground state, N equals 1, N equals 2, N equals 3 and so on is excited state. The arrow shows that an electron has made a jump from ground state to the next level up, N equals 1. If each level has an energy value, it is easy to see that the difference between the energy levels must equal the energy delivered by the photon. Thus gives our equation HF equals E1 minus E2, where HF is the energy, E1 is the energy needed to be at level 1, and E2 is the energy needed to be at level 2. Note that there is an alternative method to exciting electrons. If you hit them with other electrons, they can give just the right amount of energy from the collisions to make the jump. So here we have another question, why are the energy levels given negative values? The concept here is repeated in my videos on gravitational electric fields. So consider an electron and the nucleus of an atom. They attract each other, as you know, due to their opposite charge. As a result of this attraction, the electron has potential energy. As the electron moves away from the nucleus, this potential energy increases. However, as the electron moves away from the nucleus, the increased distances makes the force due to the electrical attraction smaller. At infinity, the attraction between the two is 0. No attraction, no potential energy. So at the biggest distance from the nucleus, where you would logically expect to have the biggest value of potential energy, you find that potential energy value is in fact 0. So that means the biggest value possible is 0. Therefore, as you move back towards the nucleus and lose potential energy, you must be going below 0 potential energy, i.e. you must have negative potential energy. For this reason, all the electron energy levels in diagrams are given a negative value, showing that the potential energy at the point is less than it is at infinity. So this brings us to another question, what do the electrons do once they're excited? Electrons are rather middle-aged in this regard. They don't really like being excited. Consequently, very shortly after becoming excited, they drop back down to the lower energy state. Of course, that means that they have to lose some energy, and to do this they give out a packet of energy, which is a photon. The size of the photon equals the size of the jump that they have to make. So once again, you can calculate the expected frequency of the emitted photon using HF equals E1 minus E2. The more energetic the jumps up and down, the higher the frequency of the photon absorbed or emitted, so the further into the UV end of the spectrum the lines go. Finally, we will look at absorption and emission spectra. Because each atom has a different electron structure, each element can be identified by the photons it absorbs or emits, from its electrons moving from energy level to energy level. Single atoms give out the clearest results when you examine the spectra for different elements. That's because when they are involved in bonding with other atoms, the electrons feel influences from places other than just the atom itself. That distorts the results, so to get the best results we use gas at low pressure in vapour tubes. Shine white light through vapour of a particular element. Analyse the spectrum of the light that has passed through the vapour. It has gaps in what is otherwise a perfect spectrum. That's what's called an absorption spectra. Now, if you excite electrons in a vapour, then collect the photons that are emitted when the electrons drop from higher energy levels down to the lower levels. This will produce a series of coloured lines on a mainly black background, showing that light is only emitted at certain frequencies relating to certain jumps. That's what's called an emission spectra.